Thomas Edison was born on February 11, 1847, in Milan, Ohio, U.S. Died on October 18, 1931, West Orange, New Jersey. He was an American inventor who, singly or jointly, held a world record 1,093 patents. In addition, he created the world's first industrial research laboratory. The role of chemistry in Thomas Edison's inventions. The role of chemistry in Thomas Edison's inventions. How Thomas Edison changed the world. See all videos for this article. Edison was the quintessential American inventor in the era of Yankee ingenuity. He began his career in 1863 in the adolescence of the telegraph industry, when virtually the only source of electricity was primitive batteries putting out a low-voltage current. Before he died, in 1931, he had played a critical role in introducing the modern age of electricity. From his laboratories and workshops emanated the phonograph, the carbon button transmitter for the telephone speaker and microphone, the incandescent lamp, a revolutionary generator of unprecedented efficiency, the first commercial electric light and power system, an experimental electric railroad, and key elements of motion picture apparatus, as well as a host of other inventions. Edison was the seventh and last child, the fourth surviving, of Samuel Edison, Jr. and Nancy Elliott Edison. At an early age, he developed hearing problems, which have been variously attributed, but were most likely due to a familial tendency to mastoiditis. Whatever the cause, Edison's deafness strongly influenced his behavior and career, providing the motivation for many of his inventions. Early years. In 1854, Samuel Edison became the lighthouse keeper and carpenter on the Fort Gratiot military post near Port Huron, Michigan, where the family lived in a substantial home. Alva, as the inventor was known until his second marriage, entered school there and attended sporadically for 5 years. He was imaginative and inquisitive, but because much instruction was by rote and he had difficulty hearing, he was bored and was labeled a misfit. To compensate, he became an avid and omnivorous reader. Edison's lack of formal schooling was not unusual. At the time of the Civil War, the average American had attended school a total of 434 days, little more than 2 years schooling by today's standards. In 1859, Edison quit school and began working as a train boy on the railroad between Detroit and Port Huron. 4 years earlier, the Michigan Central had initiated the commercial application of the telegraph by using it to control the movement of its trains, and the Civil War brought a vast expansion of transportation and communication. Edison took advantage of the opportunity to learn telegraphy and in 1863 became an apprentice telegrapher. Messages received on the initial Morse telegraph were inscribed as a series of dots and dashes on a strip of paper that was decoded and read, so Edison's partial deafness was no handicap. Receivers were increasingly being equipped with a sounding key, however, enabling telegraphers to read messages by the clicks. The transformation of telegraphy to an auditory art left Edison more and more disadvantaged during his 6-year career as an itinerant telegrapher in the Midwest, the South, Canada, and New England. Amply supplied with ingenuity and insight, he devoted much of his energy toward improving the inchoate equipment and inventing devices to facilitate some of the tasks that his physical limitations made difficult. By January 1869, he had made enough progress with the duplex telegraph, a device capable of transmitting 2 messages simultaneously on one wire, and a printer, which converted electrical signals to letters, that he abandoned telegraphy for full-time invention and entrepreneurship. Edison moved to New York City, where he initially went into partnership with Frank L. Pope, a noted electrical expert, to produce the Edison Universal Stock Printer and other printing telegraphs. Between 1870 and 1875, he worked out of Newark, New Jersey, and was involved in a variety of partnerships and complex transactions in the fiercely competitive and convoluted telegraph industry, which was dominated by the Western Union Telegraph Company. As an independent entrepreneur, he was available to the highest bidder and played both sides against the middle. During this period, he worked on improving an automatic telegraph system for Western Union's rivals. The automatic telegraph, which recorded messages by means of a chemical reaction engendered by the electrical transmissions, proved of limited commercial success, but the work advanced Edison's knowledge of chemistry and laid the basis for his development of the electric pen and mimeograph, both important devices in the early office machine industry, and indirectly led to the discovery of the phonograph. Under the aegis of Western Union, he devised the quadruplex, capable of transmitting 4 messages simultaneously over one wire, but railroad baron and Wall Street financier Jay Gould, Western Union's bitter rival, snatched the quadruplex from the telegraph company's grasp in December 1874 by paying Edison more than $100,000 in cash, bonds, and stock, one of the larger payments for any invention up to that time. Years of litigation followed. Although Edison was a sharp bargainer, he was a poor financial manager, often spending and giving away money more rapidly than he earned it. In 1871, he married 16-year-old Mary Stilwell, who was as improvident in household matters as he was in business, and before the end of 1875, they were in financial difficulties. To reduce his costs and the temptation to spend money, Edison brought his now widowed father from Port Huron to build a 2.5-story laboratory and machine shop in the rural environs of Menlo Park, New Jersey, 12 miles south of Newark, where he moved in March 1876. Accompanying him were 2 key associates, Charles Batchelor and John Croacy. Batchelor, born in Manchester in 1845, was a master mechanic and draftsman who complemented Edison perfectly and served as his ears on such projects as the phonograph and telephone. He was also responsible for fashioning the drawings that Croacy, a Swiss-born machinist, translated into models. Edison experienced his finest hours at Menlo Park. While experimenting on an underwater cable for the automatic telegraph, he found that the electrical resistance and conductivity of carbon, then called plumbago, varied according to the pressure it was under. This was a major theoretical discovery, which enabled Edison to devise a pressure relay, using carbon rather than the usual magnets to vary and balance electric currents. In February 1877, Edison began experiments designed to produce a pressure relay that would amplify and improve the audibility of the telephone, a device that Edison and others had studied, but which Alexander Graham Bell was the first to patent in 1876. By the end of 1877, Edison had developed the carbon button transmitter that was used in telephone speakers and microphones for a century thereafter. The phonograph. Edison invented many items, including the carbon transmitter, in response to specific demands for new products or improvements. But he also had the gift of serendipity. When some unexpected phenomenon was observed, he did not hesitate to halt work in progress and turn off course in a new direction. This was how, in 1877, he achieved his most original discovery, the phonograph. Because the telephone was considered a variation of acoustic telegraphy, Edison, during the summer of 1877, was attempting to devise for it, as he had for the automatic telegraph, a machine that would transcribe signals as they were received, in this instance in the form of the human voice, so that they could then be delivered as telegraph messages. The telephone was not yet conceived as a general person-to-person means of communication. Some earlier researchers, notably French inventor Léon Scott, had theorized that each sound, if it could be graphically recorded, would produce a distinct shape resembling shorthand or phonography, sound writing, as it was then known. Edison hoped to reify this concept by employing a stylus-tipped carbon transmitter to make impressions on a strip of paraffin paper. To his astonishment, the scarcely visible indentations generated a vague reproduction of sound when the paper was pulled back beneath the stylus. Edison unveiled the tinfoil phonograph, which replaced the strip of paper with a cylinder wrapped in tinfoil, in December 1877. It was greeted with incredulity. Indeed, a leading French scientist declared it to be the trick device of a clever ventriloquist. The public's amazement was quickly followed by universal acclaim. Edison was projected into worldwide prominence and was dubbed the Wizard of Menlo Park, although a decade passed before the phonograph was transformed from a laboratory curiosity into a commercial product. The electric light. Another offshoot of the carbon experiments reached fruition sooner. Samuel Langley, Henry Draper, and other American scientists needed a highly sensitive instrument that could be used to measure minute temperature changes in heat emitted from the sun's corona during a solar eclipse along the Rocky Mountains on July 29, 1878. To satisfy those needs, Edison devised a microtassimeter, employing a carbon button. This was a time when great advances were being made in electric arc lighting, and during the expedition, which Edison accompanied, the men discussed the practicality of subdividing the intense arc lights so that electricity could be used for lighting in the same fashion as with small, individual gas burners. The basic problem seemed to be to keep the burner, or bulb, from being consumed by preventing it from overheating. Edison thought he would be able to solve this by fashioning a microtassimeter-like device to control the current. He boldly announced that he would invent a safe, mild, and inexpensive electric light that would replace the gas light. The incandescent electric light had been the despair of inventors for 50 years, but Edison's past achievements commanded respect for his boastful prophecy. Thus, a syndicate of leading financiers, including J.P. Morgan and the Vanderbilts, established the Edison Electric Light Company and advanced him $30,000 for research and development. Edison proposed to connect his lights in a parallel circuit by subdividing the current, so that, unlike arc lights, which were connected in a series circuit, the failure of one light bulb would not cause a whole circuit to fail. Some eminent scientists predicted that such a circuit could never be feasible, but their findings were based on systems of lamps with low resistance, the only successful type of electric light at the time. Edison, however, determined that a bulb with high resistance would serve his purpose, and he began searching for a suitable one. He had the assistance of 26-year-old Francis Upton, a graduate of Princeton University with an M.A. in science. Upton, who joined the laboratory force in December 1878, provided the mathematical and theoretical expertise that Edison himself lacked. Edison later revealed, "At the time I experimented on the incandescent lamp, I did not understand Ohm's law." On another occasion, he said, "I do not depend on figures at all. I try and experiment and reason out the result, somehow, by methods which I could not explain." By the summer of 1879, Edison and Upton had made enough progress on a generator, which, by reverse action, could be employed as a motor, that Edison, beset by failed incandescent lamp experiments, considered offering a system of electric distribution for power, not light. By October, Edison and his staff had achieved encouraging results with a complex, regulator-controlled vacuum bulb with a platinum filament, but the cost of the platinum would have made the incandescent light impractical. While experimenting with an insulator for the platinum wire, they discovered that, in the greatly improved vacuum they were now obtaining through advances made in the vacuum pump, carbon could be maintained for some time without elaborate regulatory apparatus. Advancing on the work of Joseph Wilson Swan, an English physicist, Edison found that a carbon filament provided a good light with the concomitant high resistance required for subdivision. Steady progress ensued from the first breakthrough in mid-October until the initial demonstration for the backers of the Edison Electric Light Company on December 3rd. It was, nevertheless, not until the summer of 1880 that Edison determined that carbonized bamboo fiber made a satisfactory material for the filament. Although the world's first operative lighting system had been installed on the steamship Columbia in April, the first commercial land-based, isolated, single-building incandescent system was placed in the New York printing firm of Hines and Ketchum in January 1881. In the fall, a temporary demonstration central power system was installed at the Holborn Viaduct in London, in conjunction with an exhibition at the Crystal Palace. Edison himself supervised the laying of the mains and installation of the world's first permanent, commercial central power system in Lower Manhattan, which became operative in September 1882. Although the early systems were plagued by problems and many years passed before incandescent lighting powered by electricity from central stations made significant inroads into gas lighting, isolated lighting plants for such enterprises as hotels, theaters, and stores flourished, as did Edison's reputation as the world's greatest inventor. One of the accidental discoveries made in the Menlo Park laboratory during the development of the incandescent light anticipated British physicist J.J. Thomson's discovery of the electron 15 years later. In 1881–82, William J. Hammer, a young engineer in charge of testing the light globes, noted a blue glow around the positive pole in a vacuum bulb and a blackening of the wire and the bulb at the negative pole. This phenomenon was first called Hammer's phantom shadow, but when Edison patented the bulb in 1883, it became known as the Edison effect. Scientists later determined that this effect was explained by the thermionic emission of electrons from the hot to the cold electrode, and it became the basis of the electron tube and laid the foundation for the electronics industry. Edison had moved his operations from Menlo Park to New York City when work commenced on the Manhattan power system. Increasingly, the Menlo Park property was used only as a summer home. In August 1884, Edison's wife, Mary, suffering from deteriorating health and subject to periods of mental derangement, died there of congestion of the brain, apparently a tumor or hemorrhage. Her death and the move from Menlo Park roughly mark the halfway point of Edison's life. The Edison Laboratory. A widower with 3 young children, Edison, on February 24, 1886, married 20-year-old Mina Miller, the daughter of a prosperous Ohio manufacturer. He purchased a hilltop estate in West Orange, New Jersey, for his new bride and constructed nearby a grand, new laboratory, which he intended to be the world's first true research facility. There, he produced the commercial phonograph, founded the motion picture industry, and developed the alkaline storage battery. Nevertheless, Edison was past the peak of his productive period. A poor manager and organizer, he worked best in intimate, relatively unstructured surroundings with a handful of close associates and assistants. The West Orange laboratory was too sprawling and diversified for his talents. Furthermore, as a significant portion of the inventor's time was taken up by his new role of industrialist, which came with the commercialization of incandescent lighting and the phonograph, electrical developments were passing into the domain of university-trained mathematicians and scientists. Above all, for more than a decade, Edison's energy was focused on a magnetic ore mining venture that proved the unquestioned disaster of his career. The first major endeavor at the new laboratory was the commercialization of the phonograph, a venture launched in 1887 after Alexander Graham Bell, his cousin Chichester, and Charles Taylor had developed the graphophone, an improved version of Edison's original device, which used waxed cardboard instead of tinfoil. 2 years later, Edison announced that he had perfected the phonograph, although this was far from true. In fact, it was not until the late 1890s, after Edison had established production and recording facilities adjacent to the laboratory, that all the mechanical problems were overcome and the phonograph became a profitable proposition. In the meantime, Edison conceived the idea of popularizing the phonograph by linking to it in synchronization a zoetrope, a device that gave the illusion of motion to photographs shot in sequence. He assigned the project to William Cale Dixon, an employee interested in photography, in 1888. After studying the work of various European photographers who also were trying to record motion, Edison and Dixon succeeded in constructing a working camera and a viewing instrument, which were called, respectively, the kinetograph and the kinetoscope. Synchronizing sound and motion proved of such insuperable difficulty, however, that the concept of linking the two was abandoned, and the silent movie was born. Edison constructed at the laboratory the world's first motion picture stage, nicknamed the Black Maria, in 1893, and the following year kinetoscopes, which had peepholes that allowed one person at a time to view the moving pictures, were introduced with great success. Rival inventors soon developed screen projection systems that hurt the kinetoscope's business, however, so Edison acquired a projector developed by Thomas Armat and introduced it as Edison's latest marvel, the vitascope. Another derivative of the phonograph was the alkaline storage battery, which Edison began developing as a power source for the phonograph at a time when most homes still lacked electricity. Although it was 20 years before all the difficulties with the battery were solved, by 1909 Edison was a principal supplier of batteries for submarines and electric vehicles, and had even formed a company for the manufacture of electric automobiles. In 1912, Henry Ford, one of Edison's greatest admirers, asked him to design a battery for the self-starter, to be introduced on the Model T. Ford's request led to a continuing relationship between these two Americans, and in October 1929 he staged a 50th anniversary celebration of the incandescent light that turned into a universal apotheosis for Edison. Most of Edison's successes involved electricity or communication, but throughout the late 1880s and early 1890s the Edison Laboratory's top priority was the magnetic or separator. Edison had first worked on the separator when he was searching for platinum for use in the experimental incandescent lamp. The device was supposed to cull platinum from iron-bearing sand. During the 1880s, iron ore prices rose to unprecedented heights, so that it appeared that, if the separator could extract the iron from unusable low-grade ores, then abandoned mines might profitably be placed back in production. Edison purchased or acquired rights to 145 old mines in the East and established a large pilot plant at the Ogden mine, near Ogdensburg, New Jersey. He was never able to surmount the engineering problems or work the bugs out of the system, however, and when ore prices plummeted in the mid-1890s, he gave up on the idea. By then he had liquidated all but a small part of his holdings in the General Electric Company, sometimes at very low prices, and had become more and more separated from the electric lighting field. Failure could not discourage Edison's passion for invention, however. Although none of his later projects were as successful as his earlier ones, he continued to work even in his 80s. Legacy. The thrust of Edison's work may be seen in the clustering of his patents: 389 for electric light and power, 195 for the phonograph, 150 for the telegraph, 141 for storage batteries, and 34 for the telephone. His life and achievements epitomized the ideal of applied research. He always invented for necessity, with the object of devising something new that he could manufacture. The basic principles he discovered were derived from practical experiments, invariably by chance, thus reversing the orthodox concept of pure research leading to applied research. Edison's role as a machine shop operator and small manufacturer was crucial to his success as an inventor. Unlike other scientists and inventors of the time, who had limited means and lacked a support organization, Edison ran an inventive establishment. He was the antithesis of the lone inventive genius, although his deafness enforced on him an isolation conducive to conception. His lack of managerial ability was, in an odd way, also a stimulant. As his own boss, he plunged ahead on projects more prudent men would have shunned, then tended to dissipate the fruits of his inventiveness, so that he was both free and forced to develop new ideas. Few men have matched him in the positiveness of his thinking. Edison never questioned whether something might be done, only how. Edison's career, the fulfillment of the American dream of rags to riches through hard work and intelligence, made him a folk hero to his countrymen. In temperament, he was an uninhibited egotist, at once a tyrant to his employees and their most entertaining companion, so that there was never a dull moment with him. He was charismatic and courted publicity, but he had difficulty socializing and neglected his family. His shafts at the expense of the long-haired fraternity of theorists sometimes led formally trained scientists to deprecate him as anti-intellectual. Yet he employed as his aides, at various times, a number of eminent mathematical physicists, such as Nikola Tesla and A. Kennelly. The contradictory nature of his forceful personality, as well as such eccentricities as his ability to catnap anywhere, contributed to his legendary status. By the time he was in his middle 30s, Edison was said to be the best-known American in the world. When he died, he was venerated and mourned as the man who, more than any other, had laid the basis for the technological and social revolution of the modern electric world.